Welcome. In this video, we address the failures in classical mechanics that led to the development of quantum mechanics. We know that at the beginning of the 20th century, there were several experimental observations that perplexed scientists. They didn't really know how to explain them using the framework of classical mechanics. Among those failures was a description of black body radiation, a relatively simple phenomenon, but yet scientists didn't have an acceptable explanation for it based on classical mechanics. Then there was also the photoelectric effect. This was another phenomenon that defied classical explanation. And these two together, along with other experimental observations, led to the concept of wave-particle duality. Then finally there's atomic spectra, something of course that we use as chemists on a regular basis to determine structures of materials and identities of materials, but yet at the beginning of the 20th century, scientists really didn't have a good explanation for what was going on in this situation. So we start our discussion by asking the simple question, what is light? We know from Maxwell's work at the end of the 19th century that light is oscillating electromagnetic radiation. It behaves like a wave, it has wave-like properties, and that wave consists of two components, an electric field and a magnetic field. So we can see an oscillation here of the electric field and the magnetic field, and they are oscillating perpendicularly to each other. When we talk about waves, of course, we talk about basic properties of waves. So we have a wavelength of the wave represented by the Greek symbol lambda here. That simply represents the distance between like points in the wave. So here we see the distance between crests. That would be the wavelength of the wave. We also talk about the frequency of waves when we're talking about waves. And the frequency is simply would be the number of waves passing a fixed point in 1 second. In this case, the frequency, of course, is going to have units of inverse seconds or hertz. Waves will have units on the order of nanometers if we're talking about visible light, but generally we're talking about distance, so we'd be talking about meters or something like that that represents the units of a wavelength. We also know that properties of a wave indicate that the product of the wavelength and the frequency is equal to the speed of propagation of that wave. And of course, since we're talking about light, c here represents the speed of light. So having discussed these basic wave-like properties of light, which is where scientists were in terms of their theories at the beginning of the 20th century, we start to look at some of the phenomena that defied those explanations. And the first of these is black body radiation. This is a relatively simple phenomenon, and we observe it when we heat a piece of metal. We'll note that as that piece of metal gets hotter, it begins to glow in the visible region of the spectrum. And first it will glow red, and then it will glow orange, and then yellow, etc. as it gets hotter. That simple shift in the color, which corresponds to a shift in the wavelength emission, defied explanation. Here we have a graph that shows that basic shift. If we look at what we're dealing with here along the vertical axis, is essentially the intensity of the emission from the object as it is heated as a function of wavelength along the horizontal axis here. And we have two plots. The blue line here, curve, shows the emission at 4,000 Kelvin, and the red one is the emission at 3,000 Kelvin. Now, one thing you'll notice right away is, of course, that the 4,000 Kelvin emission is, in fact, much more intense than the 3,000 Kelvin emission. So if we heat it, the more you heat it, the more intense the emission you get from that. That kind of makes sense. We don't have any issues with that we see this increased emission. Where we begin to have issues is, of course, this wavelength shift. So if you look at the maximum corresponding to the particular curve, we'll notice that the maximum for the 3,000 Kelvin line is at higher wavelength than the maximum for the 4,000 Kelvin line. And this is what defied explanation. And this, of course, is consistent with our discussion about the shift in the emission spectrum. What we're seeing is that the emission spectrum shifts to lower wavelengths as the object is heated. Wave-like properties of light would not predict this phenomenon, and therein lies the problem. So scientists who tried to explain blackbody radiation using wave-like properties determined the equations that worked at high wavelength and low frequency, but not at low wavelengths. And in fact, what that led to something called the ultraviolet catastrophe, because if we take the simple expectations of classical wave-like behavior, we would expect the intensity of radiation, again, which is plotted along the vertical axis here, and this time we're talking about frequencies. So if we plotted the intensity versus frequency, we would see that the intensity would grow to infinity as the frequencies went to higher values. There was no maximum that we see in the real experimental observations. So the classical mechanics predicted behavior that was not observed in the laboratory. So how do we deal with that? Well, in 1900, Max Planck decided that since classical mechanics could not explain the observations of blackbody radiation, that he'd just take the data and try to fit it to an equation. He'd find the equation that fit the data and then try to explain it based on that. So Planck comes up with this equation here, and in this equation there is a constant, h, which was heretofore unknown, and now that's a constant that we now call Planck's constant. In this equation, we again have what's called the spectral density here on the left side of the equation. On the right side of the equation, we have the frequency of the radiation, nu. We have the speed of light, c, all right? And then we have Planck's constant, the frequency. And we have something called Boltzmann's constant. And then we have the temperature in Kelvin. So this was the equation that Planck derived to fit the blackbody radiation. Question is, what does it mean? Well, what it seemed to indicate was that the energy was proportional to the frequency of the radiation. So here we have this simple expression here, where n would represent the number of quanta of light emitted. H, of course, is Planck's constant, and nu here is the frequency. So the energy is proportional to frequency, and that again is not consistent with wave-like behavior, because the energy of a wave is proportional to the intensity of the wave, which is proportional to the square of its amplitude. So this concept that energy is related to frequency is not typical of a wave. It indicates that we've got something other than a wave when we're dealing with these phenomena. And again, what we're talking about here is that it looks like we've got packets of light energy emitted, or quanta of light energy emitted by the black body. And those quanta, as I said, and I will continue to emphasize this, would be proportional to frequency. All right, so blackbody radiation seemed to indicate that light had energy-like behavior that was related to its frequency and not the amplitude of the wave, which is what we would consider for a wave. Then we had the photoelectric effect. And in the photoelectric effect, what you have is a situation where light will strike and that's represented by the waves here. Light strikes a metal surface, and that light will then cause the ejection of electrons from that metal surface, and you can set up a device where the ejection of the electrons then creates an electrical current that you can easily measure. So that's a photoelectric effect. Light coming in, striking a metal surface, causing the ejection of electrons. And if we start to look at the data associated with that, by measuring the kinetic energy of the electrons, we observe this behavior. What we'll see is that the kinetic energy of the ejected electrons, first of all, there's a threshold frequency. So we have, again, kinetic energy along the vertical axis, frequency along the horizontal axis. And we'll note that below a certain frequency, which we will call the threshold, there are no electrons ejected. Once we reach the threshold frequency, we'll see that electrons are ejected and that the kinetic energy of the electrons depends on the frequency. As the frequency increases, the kinetic energy of the ejected electrons also increases. All right? So we have this frequency dependence where energy is related to frequency. Does that sound familiar? It's what we saw for black body radiation. With black body radiation, we noticed that the energy was dependent on the frequency of the radiation that was emitted. So we see a similarity here. The other thing that's interesting to note when compared to what we'd expect for a wave is that for a wave, we might expect that the energy of the ejected electrons would depend on the intensity of light striking the surface. In this case, obviously it doesn't. The energy of the ejected electrons depends on the frequency but not the intensity. But what happens is that in this case that the intensity of light striking the surface actually affects the number or the amount of light, the number of electrons that are emitted. So the more intense the light, the more electrons are emitted. But the higher the frequency, the higher the energy of those ejected electrons. So let's repeat that. Higher frequency means greater energy of the ejected electrons. Higher intensity means more electrons ejected. So we have this equation for the photoelectric effect, which relates the kinetic energy of the ejected electrons, 1/2 mv squared, to the energy of the light striking the surface, or the quantum of light, the packet of light striking the surface, h nu, which you'll recognize from the Planck equation for black body radiation, minus this term here, which is the Greek character phi, which corresponds to the threshold energy, and that is the minimum energy required to eject the electron. We also call this the work function. And you could consider it to be also the ionization energy, the minimum energy required to ionize and eject an electron. And of course, the threshold energy corresponds to the threshold frequency right here on the graph. It was Albert Einstein who actually developed this theory of the photoelectric effect based on this concept where we have packets of light or quanta of light with energy equal to h nu. We, of course, these days know that these packets of light that we're speaking of here are photons. That term was coined by G.N. Lewis in the 1920s. So this h nu represents the energy of the photon. Albert Einstein developed this theory in 1905, at the same year that he developed his theory of special relativity. That it is for the photoelectric effect that Einstein actually won the Nobel Prize. Now, this idea that we have packets of light, quanta of light, photons, would indicate that light's behaving as a particle, which is counterintuitive because, of course, there were all kinds of observational phenomena that indicated that light behaved as a wave. So this then led to this development of wave-particle duality. Here we have a situation where light would behave as a wave, and you would see, for example, and the reason for that is it exhibits interference effects, which we have not discussed in this video, but it also, we see with black body radiation and with the photoelectric effect, shows behavior that would be typical of a particle. So then we can ask a simple question: if light behaves as a wave, is it possible, and light behaves as a particle, is it possible then that we can talk about light having momentum? And the answer is yes, we can, and we certainly have experimental observations to verify this. The momentum of a photon of light, represented by the letter P here, is equal to Planck's constant divided by the wavelength. So the higher the wavelength of the light, then the smaller the momentum of that photon of light. So then we ask the question that we have particles of light with momentum. Is it possible that particles could behave as waves? Since we thought light was a wave and we could see under certain circumstances it behaves as a particle, is it possible that particles could also behave as waves under certain circumstances? So in 1924, as part of his PhD thesis, Louis de Broglie actually generated this simple relationship for the momentum of a particle. We know from physics that momentum is equal to mass times velocity. And equating that, of course, with this concept that momentum is equal to h over lambda, which we saw in the previous slide, then we could say that, just rearranging that equation, that the wavelength of a particle is then just equal to h divided by its momentum. Well, how can this be? Under what circumstances would we actually observe a particle behaving as light? Well, those experiments were carried out in 1927. Davis and Germer took an electron beam, directed it at the surface of a nickel crystal, and lo and behold, when they looked at the electrons bouncing off that crystal surface, they saw a diffraction pattern, an interference pattern of alternating light, dark, a typical interference pattern they would expect for a wave. So here we have a circumstance where electrons, which we consider to be particles, are behaving as waves with the typical interference pattern associated with waves. So this certainly seems very bizarre. Here we have the situation where light, which we thought was a wave, behaves as particles, and we have particles behaving as waves under certain circumstances. The wave-particle duality is just inconsistent with our notion of reality, but it is indeed verified by experiment. So what if we set up an experiment where we take electrons and do the double slit experiment with electrons, where we're essentially passing it through an apparatus that is very similar to what we do with double slit experiment. And we do it so that we set our electron source up so it emits one electron at a time. And so that when we look at that over a period of time, after the electrons have passed through this double slit kind of apparatus, and we see that electrons striking a screen seem pretty random here after 10 electrons. All right, and we see 100 electrons, still looks random. 3,000 electrons, we may start to see a pattern emerge here, so that after 70,000 electrons, you can clearly see this alternating pattern of light, dark, light, dark, light, dark. That's an interference pattern. So we have this situation where we have one electron at a time passing through the apparatus, and we get a wave-like effect of interference from this particular apparatus. Now this begs all kinds of questions associated with our notion of reality. Since we're only passing one electron through this apparatus at a time, what is it interfering with? And how does this electron know to go right here in order that after 70,000 electrons we've got an interference pattern? It is really quite perplexing that we can see something that doesn't make sense from our everyday world experiences. But that's what quantum mechanics is about. And that's what we are going to be leading toward based on this. We need to develop a theory that goes beyond classical mechanics that explains these phenomena. Then finally, the last issue that we're going to be talking about here has to do with atomic line spectra. We know from simple emission experiments that we have this situation where if you take, for example, in this case, hydrogen, and you pass an electrical discharge through the hydrogen gas, then you look at the light that's emitted, you will see discrete lines. Not a complete rainbow of colors. We only see emission here at specific wavelengths for the hydrogen atom. So hydrogen, we see the red, and then we see this kind of green here, and this kind of blue and violet lines associated with it, but we don't see any other colors associated with that. This discrete line pattern is something that confounded scientists because there was no explanation for it at the time. Scientists We're well aware of spectra and use spectra quite frequently to identify substances because every substance has its own special pattern of emission lines or absorption lines, depending on what we're trying to measure. And we can use those patterns as essentially fingerprints to determine identities. So scientists were certainly aware of this phenomena and were using it for identification purposes, but did not understand what it meant. And so what we have to do here is introduce the idea that atoms and molecules do not have a continuous range of energies available to them, but yet, in fact, have discrete energy levels. And of course, you know this by now, but we have the situation where we see the discrete lines corresponding to transitions between energy levels. So, for example, this red line here corresponds to a transition in the hydrogen atom between level 3 and level 2. And the color of light emitted corresponds to the energy of the photon, and the energy of the photon emitted is the difference in energy between level 3 and level 2. So we just see this discrete pattern because molecules and atoms have energy levels, and because the energy of the lines emitted is related to h nu. So we have that E equals h nu equation again when we look at the patterns here. This leads to what's called the Rydberg equation, which I won't get into right now, but we can characterize the wavelengths of the lines based on this simple concept here of a transition between levels and quantized energy levels for the hydrogen atom. And then, of course, what does that mean? Well, Niels Bohr proposed that what we had here was these energy levels corresponded to orbits where the electrons were orbiting the nucleus, but were only allowed discrete orbits. So an electron could orbit here, or orbit here, or orbit here, but it couldn't be any orbits in between. And so the energy transitions just corresponded to a situation where the atom goes from an outer orbit to an inner orbit and emits a photon of light in that particular process. So this ends our simple explanation and discussion of classical failures that led to the development of quantum mechanics. Certainly, if you would like more detail about these particular effects, you should consult your textbook and look at the specifics of all of these experimental phenomena. In our next video, we'll start to talk about how quantum mechanics came out of all of these observations.